Hello, hello. Good morning, good afternoon, or good evening for those who are living in Europe. Welcome to the second day of MasterClass that I will going to hold together with the Andrés from SOFiSTiK, Managing Director North America. If you can just tell you on the chat if you can hear us and see us well. So we'll soon start with the second portion of practical application of Grasshopper-Sofistik and Tekla. If you can write on the chat if you can see us and hear us. Yes, we can hear and see. Hello, Patrick. Welcome the second day. I remember you from yesterday. Frank is here. Ales Prima. Good to hear. Who we have here? Some people from yesterday. That's good. That we have this continuity of the master classes. So again, as always, if you can just leave a like, whatever you're watching on LinkedIn, on YouTube, or on the Facebook, just give the thumbs up. It will help us to reach maybe more people for the next webinars that for sure we are going to organize. So today it will be the day number 2. We're not going to wait for other people every time. If you are just coming late for this webinar, always remember that you can just go to preview and watch it. It will be available on the YouTube. So the first day, yesterday, it was just amazing. Already 631 people watch it on on YouTube. So we are really happy with Andrés that we managed to go to reach so many people, and actually there were lots of questions. We're a little bit. It was supposed to be 2 hours, but actually it was 2 hours and 15 minutes. But we were really glad to answer all of your questions. It was really a lot of questions, right, Andrés?
Yeah, definitely. But the more the better.
Yeah, the more the better. So today we will be more than happy to answer all of the questions. Maybe if I missed something yesterday on the yesterday session, sorry for that. But if you will write your question one more time on the chat, I'm pretty sure that we are going to display this question one more time and try to answer. So let's go to agenda for today. So again, we'll try to be in 2 hours. Maybe today we'll finish a little bit earlier. And again, Q&A session after every. So please write your question on the chat. And you, after this session, just maybe 2 hours after the session, you will get all the materials. So all the people that have registered for the MasterClass SOFiSTiK-Tekla with this QR code or this link, MasterClass SOFiSTiK-Tekla, will get the recordings on the YouTube, and also will get all the materials, the scripts that contains all the Grasshopper elements that from SOFiSTiK link, and all the elements to export elements to Tekla. So if there's, so it was yesterday a lot of question how to get all the materials. So if you got already email from me reminding about this session, so you will get after we are finished all the materials. So this is the agenda for today. First will be a little bit recap of the today's session about what we've done yesterday, maybe for those who missed that session. Next, Andrés will go to creating 3D analytical model of superstructure and superstructure, including prestressed cables. So it will be more about SOFiSTiK analysis. And then I will go to more advanced Tekla elements as a prestressed cables, reinforcement, and some of the components. Maybe we'll make some barriers and we'll try to reinforce the bridge deck. So the same software we are using, Tekla 22 educational version, SOFiSTiK Finite Element Analysis 2023. We are also using SOFiSTiK plugin to Grasshopper and Rhinoceros 7. So this is what we got yesterday. This maybe without abutments, but we managed to export to Tekla all the bridge deck, parapets, columns, and the foundation. And Andrés made an amazing script in the Grasshopper with the use of SOFiSTiK components, and we even got the PT cables extracted from Excel. So without further ado, Andrés, I will share your screen shortly so we can start and we can just continue and show how we can manage to calculate and make analysis this structure in SOFiSTiK. The floor is yours.
Excellent. Thank you. Do you see my screen?
Yes, we can see your screen and we hear you really good and loud.
Okay, great. Yeah, so today we're going to be focusing on steps 2 and 3 that you see on the screen. We already have the base geometry that we created yesterday. It was an axis-based workflow, right? So we had cross sections. We defined our horizontal and vertical alignment. We defined placements along the axis, and we were able to make an extrusion along the axis and create our 3D superstructure geometry very easily with our components. The same thing for the substructure. So today will be just, let's connect that base geometry with some SOFiSTiK structural elements. So the superstructure deck will be a structural line with some attributes, and the same thing for the piers. So they're going to be structural lines. We're going to create a 3D frame model. We'll add some support conditions, and then we'll connect this information with step 3, which is the SOFiSTiK modules. So we'll be creating some text files, basically automatically from the Grasshopper script, and we'll import these into SSD, SOFiSTiK Structural Desktop, and then run the model. So we'll get pretty much a live connection between what we see in Rhino and the SOFiSTiK FE8 model. So let's get to it. I'll exit the PowerPoint, and we can jump straight to Rhino. So Chris, can you see my Rhino and Grasshopper screen?
Yes, we can see your screen above Rhino and Grasshopper.
Awesome. Chris, you think I need to give a quick recap of the steps that we did yesterday, or should we just go straight?
Please. Yes, please give the recap. Some of the people that I joined newly, so just tell in the few words. Maybe not everyone has seen the whole session, so just please go through the steps. We have time today.
Okay, sounds good. So yeah, as I said before, this is an axis-based workflow. We define some cross sections. We define alignment data, including our placements, and we can create the 3D extrusion of the superstructure. The same thing goes for the substructure, except there are 2 vertical axes instead of the bridge alignment. So the cross sections are defined here on the left side of my script. You can see we have some superstructure cross sections. They will be the midspan section and then the pier section. We also have a parapet section, and we also have our substructure sections, which will be the pier and the foundation. So all of these sections are created externally in a JSON file. It's a text file where we can create the cross section based on a series of cross section points with variables. So I'm going to zoom in here to the superstructure cross section. We can see this component reads it from the text file, and this component will allow me to add all the values for the variables. So the girder depth is at 2,900, the width is 9,250 millimeters, and so on. So I can parametrically change any of these values, and they will, we would see immediately a response on the 3D model. Nice thing is that will also be connected to the SOFiSTiK model, so the SOFiSTiK text files will also be updated automatically as soon as I make any of these changes here. We can see the cross sections, so I'm just going to switch to a different view. So right here we see for example, this is our span cross-section, mid-span cross-section. Down here, we can see the pier cross-section, right? If I click on it, we also see the cross-section points. The cross-section points are very important because I will be using these cross-section points as a basis to create my analytical model. So, for example, if I wanted to create a curve along the axis at cross-section point 1, I have a component for that. So I just need to use the component interpolate curve and give that input of cross-section point 1, and I immediately get that edge curve. And maybe I can use that to create some barriers or some line loads later on, etc. So this is how the workflow works.
I'm just going to add some words because I'm going to use the same. It's really important what you are saying right now, because I'm going to use the same workflow to creating reinforcement. So based on the numbers on this cross section that you are seeing right now, and these numbers, I can also, as Andrés said, I can extract these lines along the bridge, and actually based on these lines, I will create the whole reinforcement in the bridge deck. So this part is really crucial and important.
Great. So I'm switching to a perspective view. I think the cross sections are pretty clear. We have the road axis, which was defined using horizontal alignment and vertical alignment. So these two components create our 3D alignment in space, and this is the basis for our bridge geometry. This alignment can come from different sources. We actually have a component that allows us to import a land XML alignment. So if you create your alignment, or if you're collaborating with the civil people and they're using Civil 3D, for example, they can export a land XML file, and you can import that land XML file through this component and use the same alignment that they are using. So if you want to work in a BIM collaboration type of workflow, this component can be very helpful. You can use any curve for your alignment, right? I can even draw it. So if I go here on a side view and I simply draw a random alignment that I'm just making up on the go, I can use a curve component here in Grasshopper to set that one curve. I need to make sure that the parametrization is correct, right? The domain should be the real length and not some other parametrization that Grasshopper did. So I always use the reparametrized curve when I'm using just standard Rhino and Grasshopper components. And basically now I can use this as my alignment, and it would probably look very funny, but let's just give it a try. Let's see. I guess I need to put my start station here. And there's our bridge. So you see, it looks very weird, but everything is parametric. Everything follows the curve. I can even go and change that curve like this in real time, and you can see how quickly everything is updated, including at the end, the SOFiSTiK FEA model would be updated. So just as a quick kind of idea to show you what can be done with this powerful workflow.
I really like the first bridge.
The first one is better. Totally agree. Okay, so the placements, they're super important too, because the placements, they define the data structure of our workflow. So yesterday, Chris was modifying the data structure at the end. So maybe for next time, we can sit down together and kind of discuss what are the important placements that we need to define, so that at the end, Chris, you don't have to make so many manipulations to the data structure, and maybe you can take it more evenly to Tekla. Or you can even, why not, have your own set of placements that you're going to be using for the Tekla part of the model, and they can be different to the ones I'm using. So we just need to create a copy of the placements, a copy of the superstructure axis, and then we kind of fork the design at this position. So why not? This could be the easiest way of working, just as an idea. Okay, so I think we can move on with the analytical model. So the substructure was, it works in the same way as the superstructure, so nothing too new there. So I'll just continue with the superstructure analytical model. And Chris, you let me know if there's any feedback or questions from the audience. Okay, so the superstructure workflow for the analytical model basically starts here. We're going to be using the same alignment, the same cross sections, the same placements as we have in the geometric model. So all of that we don't need to talk about right now. First thing I will be doing is I'm going to reach out for the interpolate curve component, which I mentioned. It takes any cross section point and extrudes it along the axis at the given position. And I can use that later on to connect that with a structural line component, with a line load component, or whatever I want to do with it. So this is how I'll create my superstructure analytical model. I'll connect the axis with the interpolate curve component. You can see already it highlights in green by default the origin of the cross section. So this is the top center of the section. It's the default setting. If I want a different cross section point, I just need to provide it here in this PTS input. But let's stay with this one because this is what I actually need. Then I will go to the structure tab and I will pick up the structural line component and immediately connect it with the interpolate curve component. So this gives me, if I click on it, you can see it gives me already all the structural lines or structural curves along the axis, and they are already separated at the placements. So this is a very important step. In SOFiSTiK, I definitely want to have this division because let's say that the first segment that we see here on the left side of my screen, it will be activated at a different construction stage than the rest. So I need to be able to define different properties to all of these different structural lines. So I would say let's take care of the grouping for construction stage analysis later. And right now, let's just focus on the first steps. So the structural line itself, it's pretty much done. You can see we have inputs here for the grouping. So that will be used for the construction stages. Again, I'll talk about that later. Then we have the input of cross-section. So I can either just give a cross-section ID that is already defined, like 101. I know ID 101 is one of the sections that I already have. So I would, for example, provide that here as an input, and I can click on the component, and it also shows me not just the coordinate system, but also that section 101. So that's all good. There's a better way, though, because the axis component, the axis definition component, this one over here, it already knows about the cross sections, right? We already have the span section and the pier section in the right order. So we can go ahead and use that information. So for the section, I can right click and I can say from axis. So if I select that option and I click again, you see it already takes the cross sections from the axis. So we see section 100 and section 101 over the piers. So that step is very, very quick and easy. The rest is not necessary. So, we're not going to change the fixation, or we don't have any hinges at start or end. The type of the element is the standard, which is eccentric beam. So this information doesn't need to be changed. The FEA size for this structural lines, I will set it up later on. So I also don't need to change that for now. So we're all set with the superstructure model. I can continue with some other things, or I can just show you already how this works if I send it to SOFiSTiK. So I actually prepared some stuff in advance, right? Again, to save some time. On the right-hand side of my script, I prepared the Aqua component, right? Remember, Aqua is the module for design code definition, material definition, and cross-section definition in SOFiSTiK. So this one is already here. We also have the SOFiMesh-C component, which is the mesher, and we also have the tendon component. So these three things are responsible for creating the text code that SOFiSTiK will later on need to run the model. So what do I have here on the left? I'm just collecting data. So I already prepared like a generic data component that will be the collection of my superstructure sections. Why did I do that? Just for to keep things clean. So I could have connected the sections directly to the Aqua component, but for me, for organization purposes, I like to use this type of things in between to keep things clean. So I connected here the two superstructure cross sections, and I connected here the two substructure cross sections. So that the section part is all defined and set up. And for the superstructure, you can see everything is orange. That means there is nothing going here in this generic data component for the superstructure or for the substructure. So I just need to start connecting some wires. So let's go ahead and do that. I will make a copy of this again to keep things a little bit clean and simple. And I'll just take this generic data component and I'll connect everything that is related to the superstructure here to keep things nice and clean. So I'll connect this one first. This, it doesn't have to be a hidden wire. I can do it as a faint wire, and it looks pretty nice to me. So I can click here, and we can see that that's being streamed straight into the SOFiMesh-C component, and I should be able to run this in SOFiSTiK and already see something. So let's give that a try. I just move to my SOFiSTiK project, and I'll go here to the data from Grasshopper, the file that I prepared, and we can see here I have include sections.dat, I have include structure.dat, and include tendons.dat. So these are the files that are streamed from Grasshopper directly into my project folder, and I'm able to read them in automatically with this simple input. So let's add the $sign here in SOFiSTiK. The $sign means please ignore this line. So I'm just going to include the sections in the structure and run it and see what we get. So right click and calculate data from Grasshopper. So it's done, and I can look at my system, and this is what I have so far. So we have the superstructure, we don't have any tendons, we don't have any substructure. We can see that the alignment is correct. So we have that horizontal curve, and that is it. Maybe I can click here on the cross sections button and show you that we actually have that change in the cross section. So we have that, the diaphragms are included basically over the piers. So far, so good. Chris, any questions so far that I can take at this time? Or
yeah, the definition of this cross section. If you just come back to this cross section view. No, in SOFiSTiK,
yes.
with the cross sections or the cross section. If you just click on this cross section to see like the profiles for each of the placements, you just had this view before,
yes, right.
This one, this one. I'm just wondering about this division because all right, we have defined the placement at the start. We have defined at the start of the column, in the middle of the column, and at the end of the column. But this is this division between all of the segments. Is it equal defined, the number? Or
this would represent the mesh.
Okay, so this is just a segment.
It's the mesh of the FEA model. I can change that. So this is usually done on the SOFiMesh-C component. So here we have a mesh size, and it is, I think the default is 1 meter. So I should be able to change that, and we should see a change. Let's try that. Let's add a 3 meter mesh size, and just run that again and see what we get.
Yeah, because I was just wonder if it was defined by another place for like a domain. Yeah, it's changed.
So you see it changed now.
Yeah, I see. Thanks.
Sure. So I said I was going to look into the construction stages later, but why not do it now, since I think it's appropriate based on the question you asked right now. So what do we have? We have this many sections. So I can look at the placements. I can see we have 10 placements, right? List from 0 to 9. That's 10 placements. That means we have 9 structural lines in total. It's just the number of placements minus 1. So what I can do is, let me just borrow this panel, and we can start defining our groups, our group IDs here. So I can say that we're going to start with 20. Let's say at the construction stage, or the group for the first construction stage will be 20, and we will have the 30 here somewhere. I will check if this is correct later on. I'll just do something quick for now. And let's say here we have stage group 40. I don't need that one. So I actually think it should be something like this. Yeah, let's just try it out. So I'm going to add this list of groups to my structural line component. Now pay attention. I have to match the data structure. So again, we can quickly look at the data structure here. So we can see that it's a tree structure. and I want to make sure that my input here is matching. So I can graft that input, and I should be able to assign these group numbers correctly to the individual structural lines. So let's just connect the wire, right-click on the group input, and graft it. So now the data structure should be matching. I can click on the structural line component, and we can see that we have group 20 in the beginning. Then we have group 20 over here. I think this is already the next construction stage. Chris, do you know that? If this segment right here is going to be the next construction stage?
Correct. It's going to be from the right to the left. So it's no, it's together with the previous one. I don't. Sorry, but can you bake the text or to see it, because it's not that clear?
So it says group 20 here, and then group 20 here left of the pier.
No, it will be not, because the last on the left, it will be just the last segment, so it will be built. So if you go to from the right side, so it will be first part going outside to the column together with the cantilever from the first part, and then the same equal length with a cantilever on the second column.
Okay. Yeah. So you know what? It doesn't really matter for now to set it exactly, but I just want to transmit the idea of how this is working. Yeah. So let's do the following. Let's just go ahead and run this one more time. So now it's going to be taking that group information, and now I can change the view. I can select the view not to use one color for each material, but to use one color for each group. So if I choose this option, it shows us already how this is going to be built, right? So this is representing also the construction stages later on.
So the groups always represent the construction stages, or you can use groups for other things as well?
Yeah, they're used for many things in SOFiSTiK, the groups. So for example, for post-processing, you can tell the program, show me only certain group, or you can even like change the stiffness of certain elements in a linear analysis. You can say, please reduce the bending stiffness for group 10 by 50%, for example. So there's different things you can do. But one of those things is setting up stages. So you can tell the program, let's create a stage 10 where you activate all the groups, all the structural elements in group 10. Then we're going to have stage 20 where you activate the groups in the elements in group 30 or whatever. And you can set up your construction sequence like that based on the group IDs.
Yeah, I see.
All right. So superstructure is, I think, pretty much defined. Let's go ahead and define some supports now. So for that, I'm going to be using, let me just move this stuff a little bit to the right. I'm going to be using a different component called evaluate section, which I think we used also yesterday to define the substructure axis. So I'm going to be focusing first on the supports at the abutments. So again, if you remember, I can call any station by their station number, so like 40 meters or 100 meters, or I can just call the placement by its name, which is quite nice and comfortable. So I'm calling abutment. Let me just take a panel here. And I can type in the name of the placement, or I can type in something like this, abut and star, and that means that anything that has the letters A, B, U, T in them will be called. So I'll connect this to the station, and I immediately get only the first and the last placement. Okay, so let's start working from this point on. So I'm going to copy this component, and at the same station, but now I'm going to be grabbing a different point, a different cross-section point. So I know there is a couple of cross-section points that are exactly located at the position of the bearings. So I'm just going to call those points by their IDs, and they are CRB1 and CLB1. So these IDs, they're coming from the JSON file. You can create as many section points as you want, and you can give them the name that you choose. So that's completely up to you. So as you can see now, I'm getting those two bottom points, and I have my top point. So I can easily create a rigid link between the top point and the bottom points, and in this way, start working on our support conditions. So let's take a rigid link component from the structure tab. The A input of the rigid link will be the top point, and the B input of the rigid link will be the two bottom points. And this will create this type of triangle that is typical for this type of bridges if I want to connect the analytical line at the top center with the position of the bearings at the bottom of the cross section. So what's next? Now I'm going to keep things a little bit simple, and I'm just going to grab a SOFiSTiK structural point component, and I'm going to take the bottom points and connect them with the structural point component. And I'm going to add some properties to the structural point component, like a fixation. So in SOFiSTiK, we have some literals that allow us to define the degree of fixation. So if I say, for example, PZ, this is going to be a vertical support only in Z direction, a vertical translational support. So let's add that, and we can see the supports are being immediately added. So if I want something else than PZ, for example, I want to have PY and PZ and MX as my 3 degrees of freedom that I want to block, I just need to add that in this way. And we can see that we have the fork symbol right here for the torsion, and it's in this symbols down here are indicated that this is free to move along the longitudinal direction of the bridge. So far, so good. So this pretty much finishes the definition of the supports at the abutments. So now let's do something similar for the piers. Let me maybe actually for the piers, we're going to do a lot more on the substructure level. So I'm just going to keep it very simple and copy this component, put it somewhere down here. And the station that I'm going to evaluate is not going to be the abutments, it's going to be the piers. So pier and star. So this just gives me the 2 bottom points. Actually, just a second. Let me think here real quick. Actually, I'm just going to evaluate the top point. This is going to be the start of my rigid links, but the rest of the definition I'm going to do on the pier level, not on the superstructure level. So for now, I think we are all set. So yeah, let's leave it there. Let me put this into a group like that. And this is our superstructural analytical model. Now let's go ahead and create our substructure analytical model. So we're going to start here from our vertical axis, our 2 vertical axes for the substructure. And let's start again with the evaluate section component. We'll take it directly. It takes both of our axes because we have a data tree with 2 vertical axes. And I'm just going to take them both together. Of course, we can use here an explode tree and maybe work a little bit clearer where we separate axis 1 and axis 2 and have two separate workflows. But I think we can manage it with just one, just keeping the data structure together. So let's do it like this. I'm going to be evaluating station 0 only, just the top of the pier. So there we go. This is the top of the pier. And now I'm going to be moving this point to the left and to the right because I'm trying to define the 2 bearing points where my 2 elastomeric bearings will be positioned. I will turn off the superstructure model just so it's a little bit easier to see what's happening here. Maybe zoom in a little bit better to this area, and hopefully that's good enough. Okay, so let's go ahead and move that point. And we're going to be moving it to the left and to the right. We should be a little bit careful because we have a horizontal curve in our bridge. So we want to be moving it not in the global Y direction, but in the local Y direction. So how do we get this local Y direction? It's very easy because this component right here it represents the placement of the superstructure at the piers. And that placement includes a plane. And this plane knows about these local directions, these local X and local Y directions. So all I need to do is go and grab a Grasshopper component that will give me the 3 vectors of that plane. So I use this deconstruct plane component. Here it is. So this gives me the 3 vectors from that plane, X, Y, and Z. I'm going to be needing that Y vector. And I can connect it here. It already, as you can see, it creates a point right there to the left in the correct direction, in Y direction, but it's a unit vector. So I need to multiply that unit vector by some value to give me the position that I actually need. So we can multiply that unit vector with any value. So here I'm going to be using, let's say, 1.5 meters. And I'm going to be using 1.5 meters to the left and 1.5 to the right. So let's just use a list with the following values. We can connect it here. So we're multiplying that unit vector by these 2 values, and then I'm connecting it to the move component. So what happened here, it worked, but not exactly how I wanted it to, because for the first pier, it moved it to the left by 1.5 meters. And for the second pier, it moved it to the right. I actually want the same thing to happen on both piers. So what I need to do right now to fix that is graph this data, graph the points, so that I have, again, a tree, and that fixes my situation. And now I have 2 points to the left and to the right of both piers at the same time. Again, data structures, as you saw on yesterday's webinar, you really can't get around it. Data structures are the most important thing to understand in Grasshopper. So make sure you study a little bit about data structures so you can work efficiently in this workflow. Okay, so we have our points to the left and to the right. Now I'm going to just copy these points upwards to define the top of my elastomeric bearings. So I'm copying it, and the translation is going to be now simply in Z direction, 0, 0, and let's say 0.2 meters. So that gives me the points on the top. I could use a little bit more, maybe 0.3, or whatever we decide. So now that I have these bottom points, I can use these bottom points to create that rigid link to the top center of the cross section. So I'm actually going to be using these. Let's go ahead and look at the top point that we created earlier and create a rigid link using that top point as my A input. But now my B input will be these points that I just created from the piers. So now I have a similar fixation that I had in the abutments, except in the piers, it's coming from the pier and not from the superstructure. I hope that's more or less clear. So the advantage is that I can go ahead and change the super elevation. So I can add like a crazy super elevation, and this rotates my whole superstructure, but my elastomeric bearings stay the same. They always stay connected to the pier, which I think in this workflow is better than defining this rigid triangle out of the superstructure alone. But of course, this is up to you how you want to model these type of things. Just adding it to the group. Okay, so let's go ahead and create this elastomeric bearings. There's different ways to do that. For now, I'm just going to use, from the Structure tab, an elastic link. And I'm going to have this elastic link going in 3 directions, right? Because the elastic link allows me to give it an axial stiffness and also a transfer stiffness, but also a rotational stiffness for each of the directions. So let's start with the vertical direction. So to make it clear, I'm going to add a vector, 0, 0, and 1. So this is the vertical direction, and the connection will be between the bottom point and the top points. So let's just go ahead and give the A input and the B input. And we can see we have that vertical arrow right here. Turn off this preview so we can see it better. That vertical arrow indicating the stiffness of the vertical stiffness of my elastomeric bearing. And I can give it a value using a panel of maybe something large like 1E7. So this is my CP value, which corresponds to my vertical stiffness. We can click on the component and it gives us a preview of that stiffness right there. So vertical stiffness is all set. Let's just copy this thing 2 times to create the other 2 directions, the Y and the Z direction. Let me turn off some wires here so that we don't get confused by the spaghetti. So since this is all the same as above, I'm just going to hide those wires to keep things a little bit more clean. And all we need to do is change these directions. So this second one is going to be our local Y direction, which we already have from here. This is all we need is a unit vector for the Y direction. We have it from the deconstructed plane. So let's connect it here. That gives us our Y direction. And we also need the longitudinal direction, which we can take from here. So the only thing that is wrong or strange is that the arrow is going backwards. I like to flip that arrow, so I can right click on the input of the direction of that unit vector and simply use an expression and multiply that by -1. So x times -1 will multiply that vector by -1 and will change its direction. So we have here vertical stiffness, transversal stiffness, and longitudinal stiffness. These ones are probably too big, so I'll just reduce these numbers to make something a little bit more realistic. And maybe these wires, I can make them faint. All right, so this part should be set up, should be finished already. What are we missing? I need my analytical model of the piers. So I'm going to need a structural line here going downwards. And I also need some kind of connection between the bottom of the elastomeric bearings and the top of the structural line for the column. So I need another rigid link. So let's just find the points that we need. We're going to need the top of the pier, which, let's see how we can get it. So we already have it actually right here. And we're going to need the 2 points that we moved. So it's very easy. I just need these 2 things. And we need another rigid link component. So I'll go to the structure tab, get that rigid link. This is going to be our A input, and this is going to be our B input. And just like that, we have the connection from the bottom to the center of the pier. Great. So the only thing that's missing, and we finish our analytical model, is the columns. And the columns should be pretty easy. You saw how easy it was to create the analytical model of the superstructure. For the substructure, it should be pretty much the same. I need to go to the axis definition component for the substructure. I need to go and pick up the interpolate curve component, connected right here. So that gives us already the basis for our model. What's missing? The structural line component, which I connect directly. We can do the same trick with the cross-section. So the cross-section is already defined earlier for the geometric model. So I can just recycle that and say, please use the section from the axis. And also, we can say the direction, the Z direction, so the local direction of these structural lines, I want them to also come from the axis. In case we have a skew, or in case we want to rotate this piers in some way, I want to make sure I'm using that same local direction. So for the dir Z input, I also say, please take that from the axis. And that slightly moves that vector and aligns the piers to the superstructure. And we are ready to go. So let's put that into a group. Now we just need to collect all the data and send it to the SOFiMesh C component. So here we already started collecting some data. This is a superstructure structural line. Let's add the rigid link and the structural points for the abutments. This one too. And down here, we're going to be adding all of this information, which we can add it in the same way we did up here, but now we can change the name. Let's just disconnect all these wires and change the name of this data component to Substructure. So I'm just going to collect all this data. We have this rigid link. We have our 3 elastomeric stiffnesses. And of course, we also need the structural line for the piers and the foundation. One thing is missing. It would be some kind of support here at the bottom. So this should be pretty easy to do. I'll just take another evaluate section component from the 2 vertical axes. And what do I want to evaluate? I want to evaluate at the bottom of the 2 axes. So the station is, I just take a look at the placements. The lowest station is 21.5. So let's use a panel with the value 21.5 meters. Connect it right there. So we get those 2 bottom points. And I'll connect that to another SOFiSTiK structural point component. There it is. And we can add the fixation, which I want to fix all the degrees of freedom right there at the bottom of the foundation. So I can either provide the literal, the SOFiSTiK literal, or I can right click on this one and say set fixation and set them all. So F would be the shortcut for all the degrees of freedom. So I just created a rigid support right there. I'm just going to add this to this collection of data. And I need to make sure that I connect this to my SOFI MSHC component. And I already organized it so that I can easily just plug it into there. And we should have everything ready. So let me just double check. If I click here on this superstructure data component, we can see everything is looking pretty good. And if I click on the substructure data collection, also everything seems to be quite good. So the only thing that's missing is the tendons, but let's just make sure that we are good so far. So I will recalculate this data from Grasshopper task. And we can see that it's all looking pretty good. So again, the colors indicate the grouping. And yeah, seems good to me. I'm just going to scale down the sizes of the supports. And I think we're ready to keep going.
Yeah, it's really looking good, and it's really fast. I don't know if you can that quickly create this geometry in SOFI Plus or in Teddy.
Yeah, probably not, right? So the only thing is you have to understand Grasshopper, right, to be able to be quick and efficient here. But I think it's a skill worthwhile learning. Okay, last thing to do is the PT, the post-tensioning. We already have the geometry that we finished yesterday using the PT geometry spline component. So it's very easy. We take the SOFiSTiK tendon definition component. We connect the geometry to the tendon definition component. We have some options to add some additional data, like the ID of the tendons, the name of the tendons, the pre-stressing system, which by default is pre-stressing system number 1. I already defined that in SSD. So if I go to SSD, we can see there is already a pre-stressing system number 1 defined, which I am using 12 strands for that one. So maybe you can confirm, Chris, if 12 is too little or too much, but this is what I'm using for each tendon at the moment.
Yeah, I think 12 is okay.
Okay, so
maybe you just increase it to 19.
19 for each tendon, okay.
Yeah.
So I just changed that, but it's still pre-stressing system number 1. So in Grasshopper, I really don't need to change anything. So this one is set. We have the load case, which by default is load case 11. This is just the standard setting that we set. So we can leave it at 11. Number of tendons is 1 by default. So for each and every one of these dots that we see here, we'll have 1 tendon, which will have each, then the what did we say? 19 strands each?
Strands, yeah. Strands.
Yeah. Okay, and then we have some data for construction stages. which I think for the purpose of this webinar, we probably won't go that far, but we do have the option to define construction stages using a component where we would define the stressing stage, the grouting stage, and if needed, a removal stage for the tendons. So we'll leave that part out for now. We also have the option to define a start station and an end station. I think somebody yesterday was asking if it's possible to define the start and the end of the tendons to be different than the geometry. So it would be possible. You could have the duct being defined along the entire axis, but then you could say, okay, but I want it actually to start at a different station. And maybe you can do this in case you have unbonded pre-tensioning tendons or something like that, where the geometry, you want to define it along the entire length, but you want to make sure that that tendon is not acting on the SOFiSTiK model until a given station and then ending until a different given station. Okay, these two things will be doing that. And then we have the jacking attributes. The jacking attributes are how you want to define your jacking force. So we have different options. We have a direct input of the jacking force, where you just input the value in kilonewton, and that's the force that will be applied at the jack. Or we have something a little bit more elegant. You can use the Eurocode jacking limits. So based on a series of limits that you apply, the program will give you the maximum possible jacking force, where you still respect the limits that are given in the Eurocode. We have something similar for AASHTO. So here we have the equivalent component where you define the AASHTO limits, and it will basically optimize the jacking force so that you just, you stay just above those AASHTO limits. So this is really all we need. And we can connect the tendon definition component to what we have here on the right-hand side. And we are pretty much ready to go. So as easy as that, let's go back to SOFiSTiK and calculate that data from Grasshopper task, making sure we turn off, or we remove this $sign so that we actually include the tendons now. So I'll just run everything again, the cross sections, the structure, and the tendons. Of course, I didn't need to do that because the database was already done with sections and structure. I just needed to add the tendons, but why not? I just ran everything just to make sure that we have a fresh start. So we have some warnings saying that the minimum radius needs to be double checked. So this is something I can do later. But if we look at our system, we now have those tendons right there where they belong. Maybe one last thing I can do, I can just simply run a linear analysis. So I'm running two simple load cases, dead load and post-tensioning. So we can just see the deformation. This would be our dead load, and this would be our post-tensioning. And that's it, Chris. I think I'm done with what I wanted to show. Let's see if there's any questions.
Yeah, the behavior of the bridge looks quite good. So yeah, so you defined on the constraints in the proper way. Mm-hmm. Yeah, we have some questions. Thanks for showing this workflow and transforming all the data from Grasshopper into SOFiSTiK. Yeah, we have some questions. It was the question that was yesterday. Maybe we can show the answer for that. For a sentence length, if I wish to add, let me see, I will just put it from the question from the Patik. For a sentence length, if I wish to add the varying section, which will go from span section to the pierce section, how can I do that?
Okay, so you want to vary the superstructure height along the axis so that it's a bigger value at the pierce, right?
Yeah.
Okay, so the way to do that, I think I told how to do it yesterday, but let's see if I can do it on the fly. We need to use the variable distribution by points component. We need to take the name of the variable, which would be D. So we're basically replacing D with something else, right? Right now we have 2,900. So we need to list the variable name, and we need to give it different values at different stations. So what do I need? I need a multi-line panel with some values. So let's say at station 0, we have something. Then I don't remember what the placements are, so I might need to go and double check that. But I'll just give you a quick example. Let's say at station 50, 55, then we have, let's say 100, and then we have 150 and 200, something like that. Let's do it like this. So let's just assume these are our stations. And let's give it different values. So we had 2,900 here. And let's say at the pier, which is station 50, we have 5,000. And I guess we do need another value here. Let's say 75. Sorry, here we need 75. At station 75, we have 2,900 again. At station 100, which is our second pier, we have 5,000, and then we are at the end of the bridge. So at the end, we have 2,900 again. So I think something like this. These are our stations, and these are our values. And all I need to do is connect this to the axis definition component, and it will apply these changes based on the name of the variable D. Mm-hmm. We have a nice component that allows us to control this because, for example, right now I'm just making up some stuff on the go. I don't want to ruin my model, so I'm going to just visualize this variation. We can do that with the axis variable distribution component. So it's kind of a plotting component where I can connect my variable and it shows me this variation. So you can see this is what it looks like. I can flip it. So this is more or less what you would expect. What else do we need to do? We probably don't want to have a linear distribution. We want to have something more like a smooth curve. And for that, I can work with the tangents of the points, or I can also work with the types. So with the types, we can force this spline distribution to have a horizontal tangent to the left or to the right at given stations. So yeah, based on these two things, we can really control how these curves look. And then we can just connect it directly to the axis component and get the desired shape.
Yeah, I really love this component. It's really show clearly the way how the heights are distributed, and yeah, it's easier to work with these varying profiles.
Mm-hmm.
Okay, thanks. One question from Fernando. This workflow can be used to multi-guider cross-section bridges. Of course, I think any type of the bridges can be used for this workflow. Just correct me if I'm wrong, Andrés.
No, any type can be. Yeah, any type can be used. So the easiest is when you have one single axis. From the data structure perspective, this is optimized to work very, very easy with the one girder line. If you have multiple girder lines, it will be a little bit more complicated from the data structure perspective, but it's the same workflow. So yeah, it's no problem.
A question from Think Tank. If the bridge model is designed as a free-span bridge, how we can customize the script? Please give some insights. So basically, we add to the alignment, right? New placement, let's say in the middle of the span, and we add a new column, and we defined it our data structure in the new way. So if we are going to add new columns.
Exactly. Yeah. So all I need to do is add a new placement here in the middle. Let's try it.
Yeah, sure.
Let's try it. So I'll just create a copy of these things so I don't ruin my model. The best thing would be to have this in Excel, right? It's the easiest way to make changes. Once you hit save on your Excel spreadsheet, it updates. So I think it's the more efficient way to do it. But let's just do it here with panels. So let's say that I have a new station, which will be, let's see, somewhere. We have the diaphragm end, we have the construction joint. I think somewhere here, we can have another pier. So this will be pier 3, and this one will be pier 4. And the stations will be, let's see, we have pier 2 at, I think at 37. And we have, maybe it's better to check it here. It's going to be a little bit easier. Construction joint, between construction joint and the end of the diaphragm.
Yeah, these tags are really useful.
Yeah.
So
I'm still struggling a little bit to find the right station. Abutment 4 is 120, diaphragm end is 83.6, pier 4 is 83, 82.4 is diaphragm start, 74 is a construction joint, and I think this is pier 3. So we need something, maybe 50. We also need this addition. So without messing up my model, I'll just create a quick preview here. Oops. I need a copy of the axis definition component. Let's create the new placements. Okay, it doesn't look too bad. We have here pier 3 somewhere there in the middle. So I will use this stuff that I just created. Yeah, let's just do it like that. So these are the new placements. And you can see we have now 3 columns.
voila, nice.
So it's really just about paying attention to the placements, right? Because when we defined the piers, we were calling the placement by its name. So everything that has pier in its name, we will create a pier there. So if we just added a new label with the same name, pier 3, it's going to work. It's going to be connected. So easy as that.
You showed really nice skills to do it in the live without any preparation. So it was the test from the students.
I was sweating.
But work. Okay, last question, and we go to Tekla Ivan about the multi-girder bridge. As we talked, can we define secondary axis relative to the main axis on which we can define the beam axis?
Yes, we can. So the way I would do it is basically everything looks the same until here. And from this component on, which defines our main axis, we can just go ahead and use this offset curve component from SOFiSTiK. And we can start defining some variation in Y. And this will create our secondary axis with the correct variation. And it understands what's coming from here. So if we have some placements with skew, for example, it will also make sure to move those curves to consider the skew or the super elevation, right? So that's the way to go.
Okay. Yeah, Ivan said that it was perfect. Okay, thank you very much for showing this workflow. And now we'll go heading to work with the Tekla. I will share my screen. You can still have your camera on. I will just remove you from the live view, but you can still be with us, Andrés. And if you have any question, just write on the private chat. Maybe someone asked questions, so we can maybe answer. Or yeah. All right. So let's go to Tekla. So yesterday we get all the geometry from SOFiSTiK from Grasshopper plugin in SOFiSTiK. So we have this bridge. So yesterday we create a script, and this is the part of the script from the Substructure. Well, we changed a little bit data structure, and we got a really nice deck with the different colors for the groups. So actually we are going to build this bridge from the one axis. So the first red part with the cantilever part. Then the second, it will be movable scaffolding system, and the rest will be the last element. So in this way, we have also structured our geometry in the data tree. The same we done with the piers, with the columns, with the foundations. And after I showed yesterday how we can do the same workflow a little bit with the in order to not use items, but in this case we're really working pretty well. But I showed also the workflow how to create a cross section. So for example, I create cross section for parapets. So let's say that we have the parapets here. So we have created new cross-section with create profile, where our input is an outline, holes, if we have some holes in that, origin, and we have the name of the profile. And in the end, we just connect it to the beam component. So you can see nice and clear there is a nice parapet. And the last stage yesterday was to create the foundation. We created with the native object. So it was the foundation, and based on this foundation, we extracted some solids. So we can see here we have the Rhino view. So we have two solids. We have extracted our surfaces, and with the polyline offset, we just created a little bit wider layer of the concrete underneath the foundation. So that's it. That was the day number 1. So let's go to more advanced stuff. Let's create some barriers on the top of the parapet. So I'm using, if I'm going to Andreas' script. So he has preferred, here is the part of the parapet section, and we have also axis definition. So based on this axis definition, so actually you can see that we have nice curves that are actually defining our parapets. So I'm going to this axis definition. So actually I can use just a curve component. So this is just a visualization. This is just a curve parameter. So based on that, we will make our railings. So we can maybe just focus on the one of them. So let's just pick one of the curve. Let me see. This curve is okay. We need to join all of the curves because we have stations. So we have joined all together two, and now we have just one curve. Okay, and now we are going to use one of the component, and it will be a component for the barriers. So if we are going to test that, this component asks us to pick 2 points. So if we select 2 points in Tekla, so let's say we're going to select 2 of them, so we'll see that we will get a really nice barrier. So this barrier, this component, actually we are going to insert through Grasshopper. So we are not going to create elements. So you can see that if we are in the select object in components, so you can see that we can select every bolt, every plate, and restruct. But we are, in this case, we are going to use the whole component that was created before. Okay, so for that, we are going to use a component. It's really called component. So you will see that this is a component. We need to have a name, attribute file name, and we have to have attributes. So to search this component in Grasshopper, let's connect the component catalog. So there is a component catalog, and if we going to right click on that one, that will be picked from the catalog. On the pick from the catalog, so you will see that we will have the dialog here, and we will search for our barrier. This is the name, and we are going to connect to name. And this is, you will see that if we are going to connect to this component, the 2 new inputs will appear. So you can see we have connected and line and position. And really depends, because if component is it's defined by just 1 point, let's say we have some construction layout points, so you need to just 1 point. So here, instead of line, it will be a point. So now we'll see that this component needs lines. So actually, we are going to define in Grasshopper. Let's see, I will just hide it. They defined lots of lines that are going along this curve. Okay, so we have the line. Really easy way to check where this line is placed in Grasshopper and Tekla is to use the beam component and just connect this curve. After connection, maybe we'll define some profile. That's really quick, D5 with the diameter 5. So we will see that we have at the edge this line that was the section of the alignment from the parapet, it was defined at the edge. We can live with that. We can stay from now. We can define by this line. So I will keep this line to have it in my mind. And let's create first divide this curve into the points. So we are going to use divide distance, because usually the barriers are not dividing by the length of the curve, but the distance, because barriers are usually straight lines. So we are going to connect this curve, and we are going to use the distance. If you remember from the first section that day, we had the scale in the meters. So in this case, I'm going to divide it by 2 meters. So you will see as our output, we will get 60 points. Okay, so it will be along this 120 meters, 60 points. It's fair enough. Now we need to have the second point. You remember? Yes, as if when we defined our component, just come back that we have to define first component. So this will be the point that we have just created, and we need our second point. The distance we can define by ourselves. So let's move this point in the vector that actually is our tangent. If I'm going to display vector, I'm going to show how this vector looks like. I'm connecting that. So you will see that here we have our points, and in every single point we have I will make it a little bit, bake it a little bit. Here you can see this our vector. So actually we're going to move in this direction our point to get this line. So here we are using move component. So we are going to move point, the first points, like you see this point, in the tangent direction. So for that we are going to use amplitude component, that actually we will have this vector and how long this point will be moved along this vector. So let's say that will be maybe 20 centimeters. Like a motion. All right. So now let's come back. Let's zoom to the first point. Now we can see that we have 2 points. Let's connect them. Let's connect that with the line component that they need 2 points. So first point and the second point, and we have 60 lines, right? Here we have 60 lines. So actually we can connect them to our component and see what we will get. So we will come back to the 60 lines. We will see that this is counting and creating objects. And in the Tekla, we're supposed to see our elements. So here we can see that we have elements, but the position, maybe it's not that as we expected. Let's connect the position input here. So it will be position as an input. And let's connect that. And here we can define where is the center of this barrier. So we can change it to the middle. Let's say it's not here. And let's check it to the top, that this will be defined at the top. And now it's really looking really good. You can see that we have all the barriers going along the parapet. Maybe we can move a little bit. So let's say that maybe we are going, because we are going to have some railings. So maybe we are going to move on the plane a little bit. Here we are using millimeters, because now we are in the Tekla, which is defined by the millimeters. So if I'm going to connect, I will see that I moved in this direction, in the left side. Actually, I need the negative value. So let's change that to negative value, negative component, just to change positive to the negative. And we are going to move that. Okay. So now we have the railings here, the posts, but actually they are not straight. If we're going to check, and then with the move component, that from the one point to another point here to the top, you can see that we have some deviation. We have 40 millimeters. And this is the reason is that we have elevation, like we have our load has a curvature, so it's going with the curve. So this point, first point, is higher than the second. So that's why this component will always work like 90 degrees to this line. So actually, this is not what we need, what we actually want, what we expect. So let's change it. So what we are going to change, that the position of this point. So now we are going to move this point to the same z coordinate as in starting point. So in Tekla, if we're going to change, so we are going to change and we are going to move by this vector, so minus 8.45. So we are going to move and we will going to have a straight bar, a straight post. You can see the difference right now. So this one is aligned 90 degrees to the parapet, which in some cases can be also the case. Some of the barriers are made in this way, but this one, it will be straight because we change this hour. But we are not going, of course, change this manually for every single post. So let's change it just for this ending point. So after you remember, we move this point. I will move a little bit. Some components to make some place. I have updated components, so you can see that all the changes that I made manually are again come back to Grasshopper. So let's deconstruct this point that we have, and we're going to deconstruct also the point from the hour beginning. So we have have all the x, y, and z coordinates. And based on these two coordinates, this is coordinates for the point 1 and this one for the second point, let's construct midpoint. Construct point. Construct. Yes. We are using the same x and y coordinates for our points, but the z coordinate we are going to use to the same as the previous one. So we are going to take the z coordinate from the previous post. Okay, so now we have the point. So now let's change it, and we have 60 points, so we can just put it in our line. Let's see if we are going to change that. And now we'll see that every single post now is sticking 90. It's not 90 degrees to parapet, but to the global z coordinate. If we are going to, of course, we are not going to place our barrier like this in the middle of the parapet. So we can just go to our step a little bit before, and we can just make this line a little bit shorter. So we can extend our curve, and instead of positive numbers, actually, we can trim our curve. So let's say that we are going to trim by the half of the meter. Yeah, usually there's a half of the meter that actually this barrier are starting. So let's move it a little bit and connect that. And we'll see this component will work again. And you will see that we have at the start and at the end, we have moved our barriers. Of course, we can add some additional calculation that we have maybe just half of the meter at the beginning, and maybe in the middle, it will be a little bit longer to maintain 2 meter distance. Let's add some railing to that. Let's say so. Based on that, so we can actually use this curve that we created. Let's use another profile. Usually in the model-based project, we do not use the circular profiles because they are hard to measure. So actually we are using octagon profiles. So that 100 times 100. Let's use position and move it a little bit. So we connect our position to the middle and change the depth. Let's say we're going to have 1 meter here. Connect that. All right, so we have it. Change some maybe. Yeah, we stay with the same color. So we can maybe move a little bit to get the position. So here, something like that, and use the plane. So maybe 100 millimeters. Yeah, let's stay like that. So here we have the to our lines. If we would like to create the new one, of course, we can create the whole script here. But as I said yesterday, the best way is to keep the data tree structure. So if we are going to connect another component number to the depth, let's say that maybe 500, and holding shift, we're going to add a new line. So we'll see that we have 2 positions, and let me see, it's not creating. Okay, let's create 2 also 2 curves. So with repeat data, let's say like that. Graphing. Okay, so we have it, and now we can change the position here, and we have our barrier. So this was the workflow for the barriers. If you have any question, just go to the chat and ask about this using assemblies. I can just show you quickly a little bit about components. So as I said, you can use all the components, including bolts even, or welds, included this application. So everything can be used by the Grasshopper. So there are some of the additional information can be extracted from the component. So if you see, for example, this Tekla anchor bolts, and when you are using that in Tekla manually, you have lots of manual parameters, like anchor board type or the size. So actually, this kind of attributes can be saved as a name, some bolt underscore test. And you can see that we are using the text panel, and we can receive all this information about this particular bolt with just this panel. So this is the one way how we can change all the names of the components. So for example, if we have some complicated barrier, so we could define everything here manually in Tekla and just save it and use it through the Tekla. So this is the first way of defining attributes in the component. Second one, we can also deconstruct our component with the deconstruct component and receive all the attributes that actually already written in the panel. So when we are going to connect to the panel, so you will see that we'll get all the bar class, grade, name, and the size, and so on. So this is the second way how we can receive all the information. Second option is about that every time when we are going to save our components in our model, for example, here reinforcement end. So we will get a file with all the attributes. So if we're going to open that in Notebook, for example, so you will see that we can have all the macro attributes defined in this way. So we can easily just copy some of them and connect it to our component. And the third one way to receive all this information about the components is to use component variable importer that can be downloaded from the warehouse. So actually here you can also, just by clicking on the component, you can get all the informations. So that was about the components. They're really powerful, especially when we are using some connection, or you have like hundreds of elements that you want to like in this barrier, that we would like to do with just one click. Okay, let's go to Tendons. So we'll come back to our Grasshopper, and we're going to have Tekla open. So here we have some tendons that were defined yesterday. Let's say maybe I have some question. Yes, I have some question. There is a possibility to insert different components as a panel list. Actually, for now, it was not possible before, but actually Sebastian, who developed that, made some changes. So actually, it's going to be done, but for now, you have to use several different components. So you need to use the different components for the separate one, because they are something with the API that they are not creating these items together in the simultaneous way. So for now, unfortunately, we have to, but actually I know that they are working on that, and the next editions of the link, they will create that one. Okay, let's go to Tendons. Okay, so we have some lines here, really defined, like really good position in the middle of our web. We can see that we have used some pipe component that can be used. So here we can just push it to to Tekla, sorry, in the two different ways. So first, of course, we can, if we are going to close the cap of this one, because it's an open VRAP, so we can send it as an item. Let's do this. It will have, it's kind of big geometry, but you will see that live link is working pretty well. Another way is, of course, creating a beam object. So this is another way. We have not that complicated cables. So if we're going to use the beam ways and with some profile, let's say the profile B55, so we can also create this by the curves, and I think it will be faster. So you will see that this is, we can say, maybe 3 times faster. We can also check it by the canvas profile. Yeah, okay, it was 10 times faster. With you can see how we can compare it. We use these lines as our position of our cables, because it's a native object of the cables. If we can also use it, but you can see that this is the difference of the time, because this component works 22 seconds, which is a lot, and actually this takes a lot time. So actually, again, the native objects win. So let's stick with our native object, and maybe it's not that, like, if we have this kind of bridge that actually we are going to build in parts, so actually someone will need to stop and cut these cables here. So let's find out these 2 planes and cut it and give maybe new colors to different construction stages. Okay, so let's find it of the planes of our work. So here, when we are going to the evaluate section, when we have defined all our sections, so you will see that we have some our placement, where start axis, and we have columns, but we have also these stages. So let's say that it will be 0, 1. So there should be 1, 2, 3, 4, and 5. So it will be 1 and 5 sections. So let's take this. Let's take these planes. Sorry. Let's take these planes. So we are going to take these planes. So we're going to use the list item. Going to take this place. Let's flatten that. So we are taking correct planes. So now we have this plane 1 and plane 2. Now we are going to cut all these cables with the plane 1 and plane 2. Again, we are going to work on the data trees, because 2 planes are going to cut all these cables. So use component that is curve plane. Now let's connect all the curves, and let's connect all the planes. Okay, so we actually get something. We have some points here, actually in one axis was quite good, but another axis is just a 1 point. So it's something is wrong. You can also, on the display and plane size, actually you can change a little bit. So maybe to 10. So we'll see it much cleaner. So we have this one and just the 1 point. And if something is not working, so probably it's the bad data tree structure. So let's say that if we are going to we need to cut every single tendon. So that's why it needs to be grafted. So if you are going to graft, so you will see that we get really nice points in every section, and here we got it in every section. Okay, so we have some points in the data structure. So you will see if you say param viewer, let's say with a param viewer, so we have some first branch, which is 0, 0, and second 0, 1. So this is the our first point here on our curve in the first plane, and the second is the first curve with the second plane. So let's put it all them together, so group it that these 2 points will be in the same branch. So to do that, we are going to use shift path and going to offset with the -1. So we are going to group it. So we have 2 points in every single branch. I will zoom it. So you will see right now that we have 2 points in every single branch. So now let's use the shutter component, because we have parameters here, just to make sure that we have reparametrization of the curve, and use the parameters. So now we can see if we have good structure. Let's go to perspective view. So this is our first stage. Afterwards, we can the second and the third one. Okay, it looks really good. Maybe we can flip the data. So just we have 3 branches. So instead of which we go to param viewer. So instead of data with 144 branches and every 3 elements in every single branch, so let's flip this matrix. So we will get 3 branches. Oh, we cannot flip it. Oh, okay, I can see because there's this not because it's not in the 2-dimensional. So again, let's use shift paths component. I think it's supposed to work. Again, we have some data here in these 2 branches, and let's flip that one. Okay, so we have 12 cables. So this is the one way, and here we have another one. So we can just entwine. So this is, I'm just playing a little bit with data trees. It's not that important for now. So this is the 2 ways of defining the data tree structure. But let's continue with that. And now, well, let's connect that. We have now 3 branches with the 144 cables. So let's connect that to the curve. Okay, I have not connected that yet. So I will connect that, all the components, and let's create also some attributes, part attributes. And again, with some colors, let's say create class with 100, 200, and 300. And as yesterday, we are going to use multi-line data, and we are going to graph the tree. And we are going, the best way is to repeat the data. So the same number as we have here, we are going to repeat this data. So we're going to repeat data by the length, by the data, and the length, it will be the same as our tree. We're going to use tree statistic, and we're going to use this length. And of course, everything grafted. Okay, of course, you will get all the scripts, so you can slowly go through and check all the data trees. Now I'm just want to show as much as possible. So let's connect that to the class and go to the attributes. So now we are creating polybeams as a object 332, and just maybe just show all of this geometry with our model, show only selected. So now you can see that we have our geometry in different colors in every single stage. Okay, this is what we wanted. We want to divide it because actually this is how we are going to divide our cables on the bridge. So usually we also divide it into different parts as an IFC and with some attributes that at the construction site it's easier to sort it out. So let's add something to this part. Let's add some anchorage. So let's use that one. So anchorage. So we are going to place some blocks at the end of the cable, and now you will see that every single cable is coming to the end with a different angle. So every single ending will be different. So that's why here parametric design will be used. We are going to use that because instead of doing every single block manually, now we're going to get all the blocks automatically. So we have already our panel evaluate curve. So we are going to evaluate curve at the start, at the 0, and at the 1 meter. Usually in the pre-stressed structure, we have this part straight, just to have the correct anchorage. So let's create already some. We have a point here. We have 2 points. So let's use interpolate component that actually will connect these 2 points together. So we have our lines. So basically, we can use our lines to our blocks. So let's say that we are going to use a beam component, steel beam, this curve. Okay, so we have some beams, but maybe not what we expected, but let's change the position in the middle. Let's say position. And let's have some profile. Okay, so now you can see that we have it. We have some anchorage. Maybe we'll change a little bit. Maybe we have another. Yeah, it's looking way better. It looks like kind of proper one. So let's do that. But you will see that something here is missing. So here, maybe in this part, we need to some concrete, because usually that we need to make some details here. And many people actually thinking that Grasshopper and Tekla can be used just to get a huge dimension, huge bridges, and the details are actually made manually. But here I will show you how you can do it really easy. This all kind of detail work with the use of Grasshopper. So let's use the same curve here, but let's actually make this curve in the another direction. So actually something that is sticking out. So here we are going to, I will just show you, create some element that actually is going, see, I will just move it. I will move it by this vector. So here, I cannot just move it. Yes, I click it here and just move by these 2 vectors. So I will create some kind of elements that are actually sticking out in order to make a cut inside. So you will see that you can see just of the part of our PT cable. So let's make this cut with our block. So based on this curve here, we can create another point. So let's move our point. So let's say that we are going to move the first point by maybe the same curve. I will make some simplification here. Here looks good, and let's create a line. I will just show you the workflow here. So this is the first point, and this is the second point, and let's create another curve. Let's see. So this is not that good. So let's flip that. Flip curve. I will use flip curve component and use the motion. So here, let's change it to what will be the size, maybe 200 times 200 in the panel. I'm not sure. Yeah, maybe it's okay. Maybe let's make it a little bit bigger, so it will be bigger, the bigger horse. So let's make 300 times 300. Okay, so now this block looks pretty good. So now let's make a cut. So let's make a cut of our blocks. Let's make a part cut. And let's use our manually. We are not needing to search for these elements. So we are going to cut these two objects. So let's say that we are going to cut this and this object. So we have our two items, and we have these cutting parts. So let's make this flatten, and let's make this all the cuts, and let's say also delete these elements that we are going to make a cut. So let's grab that. So now we are creating. So you will see that now for every single anchorage, we made our cut in that. So this is the one way of making. So this is where we made the cut at the top. So it looks really good. The red arrow is because that of the top deck. So just maybe just focus on the just one here. Just make all the cuts here. So another thing that I'm going to add is going to add this part that is actually sticking out from that. So let's create similar beam, but actually in the another direction. So let's use something like that. But this one, I will just I will change the motion. So here without moving. So now you can see that I have already created some elements that are sticking out. So that looks really good. So now we have this cut on the top, and we have some sticking out. And let's maybe at the end create some plate. Maybe we are going to use some object. Let's create maybe a round plate with some thickness. And so let's use the same component as we have it here. So let's copy everything here, but we are going to use different amplitude. I'm going to just fast and make it. Maybe not the cleanest way, but I would like to just show you how you can do it quickly. Some here 0.005 maybe. Add some motion. Maybe 5 it's too big. Okay. Let's use that one, and maybe some dimension. So the plate maybe a little bit bigger, 250. Okay, so this is anchorage. So this is what we've done. You can see that every single anchorage now system has the different angle by the end, and we have the different distances that are sticking out. So actually, you can basically done this for every single part when you are cutting your elements. If you have any question to the tendons, just go to the chat. We still have 15 minutes left. So now, if there's no question, we'll go to the reinforcement part. And for reinforcement, we are going to use the same components that actually Andrés was showing us. We are going to interpolate our curve. So let's come back to our, maybe I will make a little bit bigger first right now. So we'll see all the section. Let's zoom it. Okay, so we are coming back into this section. So now, based on this section, we are going to create all the reinforcement. So for reinforcement, we are going to work on the curves. So based on the curves from the one line as a tapered to the second line, we are going to make reinforcement. And based on these points, when we are going to zoom it, so we will see that, let's start with the bottom reinforcement. So let's, from the left side, so it will be number 17, and the right side, you have the number 18. You can all, of course, use the another points if you have looking for another section, but this is really advantage to have this additional like bottom C or this point, which is actually extension of this line, because some of the reinforcement needs to be defined by this point. So let's go with the 17 and 19. So here we have some our curves, and to just purpose of this training, we're just going to use the first section just to create the reinforcement for this MSS part, which is just this straight part. So based on that, we are going to use our reinforcement. So for that, we are going to use the rebar group component. As an item, we are going to use our part, so object in Tekla. So we are going to take that we are going to model this particular bridge deck. So it will be bottom of the bridge. Let's connect it to the part. And the shape, actually, we are going to connect this to curves. So you will see what will happen. And you will see that we have lots of strange reinforcement that is going upwards. And this is not what we are wanted to do. And of course, and again, if something is problem with the Grasshopper and Tekla, so most probably is a data tree. So this is, in this case, when we are going to use the tapered reinforcement, we are not going to graft it as here. So let's come back to that. So now we will see that we have created, all the reinforcement that is following the bridge at the bottom. So now every reinforcement that is defined by the number of points here, a number of points. This number of points is defined, can be changed by the right clicking, and they can be changed here. So let's put some attributes. Let's say cover in the same way as we will define it in Tekla. So now we can change it as well. So let's put some cover, let's say 75. You can see that we have 75 in the bottom direction. So this is because of the rule of the flip fingers in Tekla. So basically, we have to flip our curves in order to get another plane. So let's flip our curve. So make a flip curve. We are going to use that shape, and now we can have, you can see that the positive direction is upwards. Let's put some other parameters as the from plane. So we have some distances from the edges of this reinforcement, and let's connect the group. So maybe, group reinforcement, group attribute. So maybe you can put the spacing. So let's say that we have 150 millimeters, and this is it. Okay, so this is, we have the first our reinforcement. So maybe let's based on that, let's create the second reinforcement that is in the transversal direction. So maybe we can have it. So we have point 17 and 18. So that point which will still have it. Let's copy the whole part. But let's add some points. Let's say that we would like to have the points that is here and here. So if I'm going to go for the section again. So basically, we will going to look for the points that is here. So most probably it will be point 16 and 9. So let's take this point. So here we have the line 17, 18, what is in the button. Let's take as the first one 16. Okay, so we have it at the top, and the last one, I still forgot it. We have it still. It will be 11. Okay, So we have all these lines. Just to visualize that, we can always create a really quick beam in Tekla. So here, just really, so this is the lines that we are actually defined here. We have some question from Patik. Can we add shape code in reinforcement? Yeah, of course. You can create all your own shape codes here based on the lines. So actually, now I will. So this was longitudinal rebars. Now I will create transversal rebars. So I will create my own different shape code. So let's say that we are going to. We have this rebars. We are going to use that, but actually we are going to create reinforcement in the transversal direction. So to do that, we need to divide our curve. Let's see, I will just look at the time. We still have 10 minutes to go. So let's divide our curve. Divide curve by the number. Let's say that maybe just 10 numbers, it's just more than enough. And by flipping our matrix, we can actually find the points that are in the same branch. Flip matrix. If we're going to flip this point, we are going to have these branches, and with the interpolate, now we'll see we're going to connect all these points. Actually, the software connected, but we are not going to get this reinforcement. I don't know if this will create it. Let's go. Let's check it if it create. I don't know if Tekla will not crash. Let me see. Okay. So this is actually, Patrick, your answer for your question. So we can define a special code. So we can see that this is a really special reinforcement, but this is not what we are looking for. Let's change the degree here, of course, that is not the third degree, it's the first one as our input. So yeah, so here we have the reinforcement. So this is the reinforcement that is following all the whole the length of this bridge deck. Okay, so we can also change some parameters. So let's say that we have another cover thickness. Let's go to 100. Looks good. Here, let's stick with that. Of course, we can add some colors. So every single parameter that is changed with inside Tekla, actually we can also change in Grasshopper. So we have not part attributes, but the rebar attributes. And let's say the size, maybe we can change to 20. And the class, maybe some color, so we can see it nice and clear. Okay, let's create the last reinforcement for today based on the another parts of reinforcement. So let's delete that, and maybe we are going to use these curves. We are going to use actually the same part of the script. So you can see that we have created this part. So for transversal direction, so actually we can use all of this script. So let's copy that, all of the script, and just replace the lines here. If we are going to replace the lines, so basically we found the lines 13, 20, 9, and 18. Okay, so this was the lines for the this rebar. Let's say I can just maybe show this rebar, show only selected. So again, I have created all the rebars with the same lengths along the whole with the some shape. If we go to inquire, we have some definition with the size 20 that we have defined it. We have A, B, C length and the shape 4 in this case. Of course, if we are going to make it more difficult, so of course it will be shape maybe 99 or under not defined. And of course, if we are going to change it, make some adjustment, if we are going to change our cross section, our lines are changing, so the shape will be changed as well. And it's really easy in Grasshopper to make the adjustment that actually it will follow the the whole bridge deck reinforcement. So the last thing that I would like to mention is that it's really useful to add some cross-section like this sketches into your canvas. So I will quickly show you how to add it based on the, of course, SOFiSTiK. So we have our BRAP. So let's say that we have our BRAP, and actually we would like to bake it in our canvas. So let's say that we would like to use this as a curve. And let's just really fast orient that. Okay, from the plane y and z, and to the x and y. So we have it. Let's change the scale. I already know that it's a 10 factor, and let's bake it. So you can see that we have already this nice baked geometry that we have it, and we can really easy put it in our canvas. So with the pencil, we can just draw some line, and we can import our data. So let's that we would like to import, and this is our profile. So based on that, actually we can add some lines. So for example, let's add maybe the reinforcement that we created. So this is the reinforcement that is going in this direction, something like that. Let's say create something here, and let's add it. So it will be the same position. So we have created this reinforcement. We changed some colors, and this will be the easiest way to get it. Okay. Would be possible to showcase some stirrups in the parapet? So actually, it's the same workflow. Actually, if you will retrieve the information from the parapet, from this every single curve, so you can use the rest of the script based on that. So yeah, it can be good homework. Richard, you're going to get this, get the script. We are lack of time right now. But just contact if you will have some problems to get it. I can, of course, help you. Okay, is it possible to define maximum length? Hi, Tadeusz, 12 meters, for example, for 3 bars of these components. I usually model all rebars separately using some automation for lap length soles be good. Okay, so answering the question, so no, here is not automation. You can do this automation by yourself. So when you have a curve along the bridge, you can divide it as we have here divided by the number, but actually you can divide it by the length. So actually here you can divide this curve into 12 meters. And based on these 12 meters, actually you can create the 12 meters rebars. And of course you can extend it a little bit to have this overlap. So this is kind of tricking with the manual. It's not the option available by the out of the box. If you would like to use this overlapping, so the best way is to use the component, which is cast in place rebars, but actually can be used by the same components that we used with the barriers. So if you remember, we had this component catalog, and Tadeusz, you can just pick on that, and you can use cast in place. So you can main bars, and you can use it for that. So if you're going to use component, so actually you can use that component, and you can plug in. You can put plugin input. So if you have I don't know if you have experience with this cast in place, but actually you can define in this plugin here, mine rebars, all the data, and this data can be defined in Grasshopper and pushed through Tekla. So I hope it answers your question. Tobias, hi Tobias. What about multi-user in Tekla? We should work alone for such cases. What do you mean? What multi-user? We can work together with the different multi-users in Tekla, but actually, Grasshopper and Rhino do not have multi-user option. So actually, we are going to work separate on the separate screens, but actually we can push the data as we model as we model normally in Tekla. For collaboration, if we are working, for example, if your team consists of many people that work with Grasshopper on the same project, so actually we are using kind of input data component, data output, and data input. And I think this is maybe what you were looking for, data output. So actually here, few guys working at the same model in the same time. So yeah, so for example, here there's some people that actually make a reinforcement on one group of from the parapet and the second one from the let's say deck. So in this case, we usually create data output. So let's say that we are going to create data output with the parapet curve, and let's say what kind of more data we have. We are going to use some PT cables. Okay, so let's give some names. So we have nice and clear. So we have railings. Okay, we have railings, and add one more. Let's say that we have the curves here. Interpolate curve. Let's add it to this workflow. Okay, so we have this input file. So now we can just save it. I will just save it locally, this Grasshopper data file. So it's just a file that actually can be placed on the server. So let's say that we are going to place that on the server. So here, and if someone going to work, for example, your colleague wants to work another on the same time with the different part of the bridge. So actually, he can go to open the new Grasshopper file and actually right-click and take a source and actually to choose this data file that we have created. And it will take all the geometry, the same you can see with the names that we have created in the previous. So it's kind of live link if you are going to change anything. Let me see, I will come back to our workflow. So if we are going to add some data, so let's say that we are going to add, let's say at some point. Let's create a 0, point. Let's add it to this data output. And now we are your colleague going to have this going to here, and you can see that it's already updated. So it's the best way to work with the standard components in Tekla with your colleagues. I hope it helps you. Okay, Richard, thanks. Okay, do we have, how can I use the script for multi-girder post-tensioning bridge with expansion joints in the mid-section of the pier cap? It's a for SOFiSTiK script. Thank you for wonderful masterclass. I don't know, Andrés, if you are still with us, maybe you have the answer for this question. I can read it one more time. How you can use the script for multi-girder post-tension bridge with expansion joints in the midsection.
Yeah, it's basically the same workflow. So you have to put in the work to understand how the components are doing their job, but it's the same. You're going to have a section. You're going to have multiple sections, you're going to have multiple axes, and you're going to have placements that will define the start and the end of your expansion joint. So it's possible. Just maybe understand this one first, and then you can jump on to the next task.
Yeah. Okay. I think we are already p.m., so we are not going to extend it as yesterday. One more time. Thank you, Andrés, for your time, for preparation to these masterclasses. You made a extremely great work. I think people really like it. I have already lots of comments that actually like this masterclass. So again, thanks one more time, everyone who registered for this webinar will get all the recordings and materials. I don't know. Would you like to add something?
No, I think we're all set. Thank you, Chris.
Yeah. So as you can see, we can really recommend this workflow. I think that in Scandinavia right now, like most of the company actually are starting to using this workflow and having already good results. And you can see the maybe main question is that, okay, you don't have to have these huge bridges to start with this SOFiSTiK and Grasshopper workflow, because this is most of the use cases, maybe just showing like a huge bridges where you can see all this application. But actually, the easiest way is to start with the small bridges. Do you agree, Andrés?
Absolutely, yeah. The benefits of parameterization are there for the simple projects, just like for the big projects. So don't wait for that big project to start.
Yeah, because it will be it will be problems with the huge projects. So the best is to get the experience of the small ones. Okay, thank you, Tadeusz, Sahin, Ivan, so for being with us. So we keep in touch. And just follow Learn Grasshopper and follow also SOFiSTiK. Go to LinkedIn for SOFiSTiK North America. Just don't forget to leave the like there, and we'll see maybe somewhere. Thanks a lot.
Thank you.
Thank you. Bye bye.
Bye bye.